Okay, what are we doing in this problem? Well, we're going to use a proof by contradiction, so we should look back at our notes of what that is. And we're going to prove that at least one of the real numbers, a1 through an, is greater than or equal to the average of these numbers. Okay, what is that even doing? Sometimes I like to start off these proofs by just trying to convince myself that it's true and what's even going on. And first off, what is this business right here? It's a list of numbers, an arbitrary list. So we're going to be proving this for all possible lists of real numbers. So it better work for any example list we give, like maybe 1, 2, 3, 4, 5, 6. Okay, the average of that is 3.5. Okay, cool. So there are 3 numbers that are bigger than the average. Well, that fits with this proof. We're proving that at least one of them is. Now, why does this proof have greater than or equal to the average? What if we have a list of just 5, 5, 5, 5? Well, the average is 5. Okay, so it's good we have this greater than or equal to, so that 4 numbers work. Okay, I am relatively convinced to my own self that this is true. This didn't really help the actual proof at all, but it helped me figure out what was going on. And now, the first thing that seems helpful for this proof is we're going to be talking about the average of these numbers. And so I'm going to give it to myself as a variable so I can reference it in the proof really easily. And so let A be the average of my arbitrary list of real numbers. And I'm going to write what A equals directly because I'm probably going to use this fact in the proof somewhere. And so you don't actually have to write this so A equals part, but I think it's really helpful and you should. But just write down all the information we have as we get it. Okay. I also write down what I want to show in a proof because this will help me figure out what my assumption is. This will help me figure out where I'm going. It's just a really good idea. So we want to show that there exists an A sub I. So I'm going to say this is the same as saying there exists a number in our list. So exists an A sub I where this A sub I is greater than or equal to A. And I'm going to make a note that I is between 1 and n. So really this is how we go through every number in our list. You also could just write out the English version of this statement that's said in the question. I'm just writing the logic version because I don't like writing that much. Next step is we're doing a proof by contradiction, which they told us to do in this problem. But if they hadn't told us, we might figure this out by thinking about if we're doing a direct proof here, we would assume this part. And that assumption doesn't give us that much information to work with. But what do we assume in a proof by contradiction? We assume the negation of what we want to show. So when we negate an exist statement, that becomes a for all. So for all A sub I, and we then negate the inside part, and we get that A sub I is less than A. Again, I is between 1 and n. This seems like a much more useful assumption. So now this is our assumption. We're pretending it's true. We're inside our assumption box. And now we need to actually do stuff, which is unfortunate. And what should we do? Well, one of my first steps is usually to write out what this assumption is giving me in the fullest way I possibly could, just to see what I have. So this is really just, I rewrote the assumption, but we know A1 is less than A, A2 is less than A, all the way to AN is less than A. And now we need to do something with this fact. And I still might not be sure where I'm going, but we have this statement up here about what A equals, and it involves adding all of these A terms together. So that seems like a really good move. Even if I don't know how it's going to help, we used it up here, so it seems a good thing to try again now that I have more information about A1 through AN. And if we sum them up, each term is less than A, and there are n terms, so this is less than n times A. Well, this is cool now. What if I divide both sides by n? Now this statement is less than A. And then if I plug in what A is equal to, which I remembered because I wrote it for myself up above, whoa, this is not going to work. This is a big false. Oh no, I hit the wrong button. Come back. Okay, I'm back. This is a big false. So our assumption did not work, got to a false. So by contradiction, we have shown that our assumption is false, so the negation of our assumption is true, which gives us what we wanted to show in the first place. And we're actually done. That's it. We did it. But I think one thing I want to point out is we really used natural deduction here. I know. Stay with me. We did. We had no premises, which is fine. We just start with an assumption. And our assumption was the negation of what we were trying to conclude at the end. So our assumption was the negation of this. We did a bunch of work and we got to a false. What natural deduction rule does this look like? This is a not intro. So I can pull this outside of the assumption box. And then, double negation cancels, and that's what we wanted to prove. This is entirely the format of a proof by contradiction. It's really a not intro, natural deduction. Same logic, we just used a lot of words to show it. And we did it. So the last thing I want to point out is this is the official Rosen solution. Rosen is our textbook, official textbook solution to this problem. Feel free to read through it just to see another example of how you could write this out. And good luck with the rest of the proofs in this lecture.